I think this is, should be flashing. Okay, so this is going to vibrate at a certain frequency. Now, this is going to, when it vibrates up, it is going to send a wave down there. When it reflects back from here, it's going to be underneath. So when they collide perfectly, one going this way, one coming this way, it's going to be constructive interference and it's going to cancel out. So that then is right here, right? So right now, that is 1, 2.5 waves. Right? There's 2.5 waves up there. 1, 2, yeah, 2.5 waves. Now, that's still 2.5, isn't it? Let me turn this. Hang on, Riley. You're about the right distance here. Now, how many waves there? 1, 2, yep, 3, I think, right? But these are nodes where you can put your actually hand right there where it's constructive interference. So that is superposition. That's also going to set us up musical instrument waves coming up. So we are on chapter 17 now, which is going to do sound. So that should be all. It actually starts right here. So I've got 16 and 17 all in one shot here. So let me show you some introductory video clips here for sound. So of course we know this. Here's the one that I keep forgetting and I can't find it normally. This is what Hollywood has to fix. So they blow the side of this mountain up. I don't know. It doesn't look like a rock quarry. They're doing a big detonation here. And obviously the camera is far away from the explosion. So you wouldn't sit and watch a Hollywood movie and listen to this delay. People would complain. So watch this. The side of the mountain is going to blow up because you're visually going to see it first. So Hollywood's going to redo this. What's that? In old movies, yeah, the delay was there.
The air around the string is made up of molecules. As the string moves, the air pushes against the molecules that are in its way, holding them together and pushing them against the molecules to them. And those molecules push against the next one.
So this is your compression region here. And when it flexes back, it's your rarefaction where there's a lot less air molecules. So that's a sound wave traveling.
The string makes sound waves that travel through the air, very much like ripples in the pond. When these waves reach out here, they make tiny bones of ears to vibrate, and here's sound. If we pluck our guitar strings, we'll put the air molecule gently and a soft sound. If we pluck hard, it crowd molecules.
Right, we pluck it hard. We're just pushing that string a farther distance, which is going to flex back this way a farther distance, which is going to be louder because it's just going to push more air, right? But the frequency and speed are going to be the same in this case. Speed's going to be the same. Frequency's going to be the same. Amplitude's going to be, this is really amplitude. But you're plucking the same exact string, same exact frequency. Speed's the same. The speed of sound is going to, no, the speed of sound.
Together and make loud sound.
That was this one, I think.
Energy, a vibrating object, moves through the air in waves. When these vibrations in the air reach our ears, interpret them as sound.
So we're going to suck all the air out of this jar. And of course, sound needs a medium to travel through.
Now, so the air is gone. Can we hear it? The sound of this axe moves through the air in all directions. A distance, the sound arises.
So this is measuring the speed of sound in air. Now, this says it's shot at 24 frames per second. You could actually play this back frame by frame, and when you hear the smoke, or excuse me, see the smoke, and then hit the frame button, frame by frame by frame, when the sound hits, you can get the frame number. You could actually measure this.
We'll use a starting gun as our source of sound.
So in the starting gun, you see the smoke come out right away, correct? Does that show up on the screen? A little bit. No. Now you have a stethoscope and a hammer. 300 meters previously was through air, now it's through steel railroad tracks. It's going to travel faster through the steel railroad tracks. It is. Anything more dense, it's going to travel faster through. Here's your generator right here, Bob. So this is at 2,000. So this is times 100 on here. Frequency increases, wavelength decreases, right? Frequency increases, wavelength decreases. I think I did that one. Okay. So we'll go until we get to Doppler. How do I end up with a pen open on this? Okay. So on this slide, we need some kind of mechanical vibration and some kind of medium through which it can go through. So we looked at some videos. Everything's caused by a vibration. And this is the equation we'll use for the speed of sound. This is the correction factor for the temperature. And this one's easy because it's in degrees Celsius. Then this chart, let's see how good this printout is. It's not bad, I can read it. So in air, this is the speed of sound in meters per second. This would be, looks like about 0 degrees Celsius, 331 in air, 259 in carbon dioxide, pure oxygen 316, helium 965, hydrogen 1200. Here's liquids. Here's liquid water, 1480. So 4 times faster in water. Then when we go to solids, here's glass, 5640. It looks like lead, 1960. Aluminum, 5120. And steel, 5960. So a lot faster in metals than in air, than in water. Yeah, every problem you're going to have to adjust for the temperature of the air. And that's the first problem we do right away. Where is that, baby? Yeah, 17.1. So it says calculate the wavelengths of sound at extreme audible ranges, 20 to 20,000 hertz. So this is going to be your low frequency, right? And typically, you're not going to have a speaker that's going to put out 20 hertz. I don't think you're going to hear 20 hertz either, but maybe you get up to 60 or 80. And 20,000, you're not going to have a speaker to do 20,000 hertz either. But this is the range. So first of all, at 30 degrees, what should be our velocity of our sound is going to be 331 meters per second plus, I'm just going to put 0.6 times 30. That's going to give us another 18, isn't it? 18. So 331 and 18 puts us at 349. So the speed of sound at 30 degrees should be about 349. So if we do, we know that the velocity of sound is equal to wavelength times the frequency. So 349 meters per second is equal to the wavelength at 20 hertz. So my wavelength here at 20 hertz, 349 divided by 20 is 17.45 meters. 57.3 feet. Now, at 20,000 hertz, at 20,000 hertz, my wavelength is only 0.017 meters. Oops, I just put a little over ½ inch. Yeah, 0.017 meters. High frequency, right? Short wavelength. Lower frequency, much longer wavelength. If one goes up, the other one goes down, and so on. Okay. Now, how about sound intensity? So, audible sounds, again, we're saying from 20 to 20,000 hertz. That depends upon your age and whether or not you even have the ability to have a device to put out those frequencies. 20,000? I would never hear 20,000. You can have your phone try to do it? Is there an app that'll... YouTube has it? I do. I have Alexa play white noise once in a while in the background, which is just a combination of frequencies. Works out pretty well. Okay, infrasound waves having frequencies below the audible range then. So these are going to be less than 20 hertz. Ultrasound waves having frequencies above, so these are going to be greater than 20,000 hertz, obviously. But now intensity is the power transferred by a sound wave through a unit of area normal to the distance of propagation. The hearing threshold represents the standard minimum of intensity for audible sounds. We will talk about that at a later time. The pain threshold represents the maximum intensity that the average ear can record without feeling or pain. So it actually looks like this. First of all, intensity drops off with the square of the distance. From the source. This right here? It's going to be a division. It's going to be a division. This is going to be intensity. This is going to be power in watts. And this is going to be area in meters squared. So usually we're always concerned about how far are we from the source. So we have something like this. And for these distances, they go R1, R2, R3, and so on, right? Yes, but they'll call it distance from the source more than likely. So here's an example. Intensity 1 at R1 is going to be the power of the source divided by 4 pi R1 squared. Yeah. Well, that's supposed to be a, that's the, not, yeah. Monday. No, it's not even Monday. Yeah, sometimes. This is the area of a sphere. Huh? That would make sense, wouldn't it? Sphere. That might be, this should be for surface area, I think. Might have to look that up again. This, of course, is the power of the source. Then you'd have I2, obviously, then would equal to power of the source 4 pi R2 squared, right? Just for that R. That is just for the R. Hopefully that's surface area of that sphere. Area of a sphere. Now, here's the key to this. So if the power of the source doesn't change, if I take I1 times what's down here, I would get the power of the source, right? Just like over here, if I take I2 times 4R2 squared, I would get the power of a source, right? So if we say power of source 1 equals the power of source 2, then we end up with this. I1 4 pi R1 squared equals I2 4 pi R2 squared. then what can we do? Right, we get rid of the 4, we get rid of the pi. This would be intensity 1, radius 1. This would equal intensity 2, radius 2. Just a different distance. So here we have I1 R1 squared equals I2 R2 squared for an equation going forward. I don't know how many examples, if we got power in there or not. So this is intensity then in watts per meter squared when I zoom in on this. And we'll do more of that. We'll do decibel calculations. Not a decibel. You can convert it to that, but it's a logarithmic function. So decibel levels, obviously, loud rock concert 120. Jet airplane at 30 meters. Bursting of eardrums at 160. Threshold of hearing would be 0. Huh? Now, let's go to the next page. Because this, we got to talk logarithms for a second. Everybody's favorite math, logarithms, right? But it's really easy. Logarithms are really easy. Log, here's how you remember this. Log base 10 of 100 is equal to what? It is equal to 2. Because when you put 100 in your calculator and hit log, or do log of 100, what does this 2 represent? That represents, if you take this base, how do you get 100 out of it? You get 100 when your base power is 2, right? It's returning this value. But a logarithmic scale does this. If your intensity goes up by 10, to 10, wow, 10. If I multiply that by 10, obviously, 100 times 10, I'm going to get 1,000, right? So we don't need a calculator now, because 10 to the what is going to equal 1,000. 10 to the third, right? Now this is what a logarithmic scale does, and pH is the same way. This number goes up 10 times. The log only goes up by 1. If you go 100 times more, the logarithm is going to go up by 2, right? So a logarithmic scale is base 10. This goes up by 10. This only goes up by 1. Now, by the way, if you have a math class, if you can remember this, then those dang math teachers do this to you. I just got to show you. It's, if you know that one, this is 3 because 2 to the third equals 8. They go ahead and change the base on you right away, correct? That's what those math teachers do to you. But if you can remember the order of this one, what this represents, so what? You just have to match it up, right? and you could do it. This is my base again. Okay, so sound intensity, bells, in decibels of a sound having intensity I in watts per meter squared is defined as 10 log base 10 of intensity over the reference intensity, 10 to the minus 12 watts per meter squared. This is the lowest threshold intensity for normal hearing at a frequency of 1,000 hertz. Yes. If you take this 10 here and divide it, you'd have a tenth on the other side. If you divided both sides by 10. Now, let's see. Intensity level. Let's do this in, we'll do this in decibels. Let's take this one up here. We got room up here. Compute the intensity level of a sound whose intensity is 1 times 10 to the minus 4. Log of, this is going to be 1 times 10 to the minus 4 watts per meter squared over my reference intensity. This should produce decibel level of now, what is the intensity of a 50 decibel sound? So now we've got 50 is equal to 10 log of, I'll put I sub O in my equation this time. We're going to solve for this.
So I just need a clarification.
Yes.
On that first one up there where we got 80, you got 10 times log.
Yep.
Here you could put your dot. So is it just 10 log?
Yeah, I can put,
Okay. Sorry, I just...
we can put a dot in there for now. Yep. What's the first thing I'm going to do to solve this? You could, and these logs you actually could subtract logarithms. Remember all that fun stuff? Most people hate logs, right? I'm going to divide by 10 first, huh? Let's divide by 10. So if I divide by 10, I'm going to end up with 5 is equal to log of I over I sub O. Now, if I raise both of these to the inverse log, meaning this, 10 to the 5th equals 10 to the log of I over I sub O. I wrote that correctly. Yes. I'm taking the inverse log of both sides. Now, in our calculator, you're going to have log, and then you're going to have 10 to the x. So I know that if I hit log down here and put in 100, what am I going to get? I'm going to get 2. I know that if I hit second log to get the 10 to come up, if I put 2 in here, I should get my number back, correct? So this is called inverse log, anti-log, but inverse log. If I take inverse log of both sides, the inverse log of a log is simply what the log is. So that means 10 to the 5th is equal to the intensity over the threshold intensity. The inverse log of a log. Then my threshold intensity right here is 1 times 10 to the minus 12 watts per meter squared. And if I solve this for my intensity, by just multiplying, I am going to get what? And this would be 1, by the way, times 10 to the 5th. If I multiply just by adding exponents, I'm going to get negative 7, aren't I? Aren't I going to get 1 times 10 to the minus 7? I should get 1 times 10 to the minus 7, don't I? Let's switch to this side. We got this, baby. Let's switch to the first side. I do have an intensity problem here. Let's sneak in. I've got an intensity problem that I should have did over here. But I guess I needed decibels to get it, so we're fine. What is the intensity in decibels? For a 60-watt power source 4 meters away. So we're going to use this equation up here first to get our intensity. You get watts per meter squared for, so that would be intensity. So here, Our intensity is going to be the power of our source divided by 4 pi r squared. Yep. This is going to be 60 watts divided by 4 pi and then 4 meters squared. Yes. Oh, just keep dividing. Take 60, hit divide by 4, divide by pi, divide by 16. Hit your division key. If you do this in your head, hit your division key 3 times. That's the easy way to do it. 60 divided by 4, divide by pi, divide by 16. And if you do that, you get an intensity of 0.298. Yeah, 0.298 watts per meter squared. Now I'm out of room, so I now, since I used my intensity equation, ooh, that's a beautiful looking arrow. That's a sweet looking arrow. That's not bad. Let's get to the other page now and figure out my decibels. So if I get to my other page here, figure out my decibels. From 60 watt source 4 meters away from previous, I was 0.298. So my decibels that I'm going to get that's my intensity over my threshold again. 1 times 10 minus 12. Yeah, 114.7, huh? $114.7. Now, we're going to spend some time introducing Dopplers, Doppler shift, which is the whole idea behind radar and ultrasound and many things. Who was I talking to? Another student. Now the cars have automatic braking systems. So the guy was going down the road 50, 60, 70 miles an hour. I don't know. Somebody pulled up to him, got him too close to the back end. What'd the car do? Started braking. So if you have somebody tailgating, the computer on the car was braking the car. That doesn't sound like a good idea. It's kind of like the MCAS system in the Boeing 737 MAX 8, huh? It's programmed wrong. Yes. It's I over, this is I sub O, the threshold of hearing. Uh-oh. This one right here? I'm going to do this first. Oh, sure. I'm going to do log, and it already has a left parenthesis, so I'm going to go 0.298. I'm going to divide by 1 to the negative 12. Make sure you're using the plus minus button and not the subtraction key. So I'm going to go enter there, and I'm going to times that by 10. I do the log first. You can put 10 in front of it and then log it, but does that show up pretty good? All right. I've got a YouTube listing here, but I've got some. Here's that's Doppler and shockwave. We're going to look at this first. Now, here's what's going to happen. You can have a moving source or a moving observer. Now, for example, if you're standing down on the side of the road, you're going to see a video here with a train coming at you. That's a moving source if it's blowing its horn. Sometimes you can have both moving. The train can be blowing its horn, coming towards you, and you could be driving in your car towards the train. That would be a moving observer as well. You're the observer. That you're going to hear that as a certain frequency.
The rate at which waves send out at a source is the same as the rate at which they erupt at the ether.
So this person's going to hear just the frequency of the source. Nobody's moving. Now, the source is going to move towards the person's ear. The source is going to be moving. Are they going to hear a higher frequency or a lower frequency? They should hear a high. If this starts moving towards the ear, it's going to push these waves into the ear at a faster rate, is it not?
As the source moves toward your ear, you hear a higher pitching sound.
So that's a moving source. We'll derive these equations next time we meet, but let's just look at what we're going to do first. We've got to adjust for moving sources or moving observers. And if it moves away,
The source moves away from your ear, you hear a lower pitching sound.
right, the waves are not arriving at your ear with the same frequency.
Source moves toward.
As the listener moves toward the sound, its apparent frequency increases.
That's our moving observer.
As the listener
So you'll hear this difference for sure. So listen to this train when it's right before it passes and after it passes.
Let's get some backside of the
You definitely hear a shift in frequency there. This one here is a big difference. You hear that difference? We'll be playing back choppily. This one's pretty obvious. This is a moving observer. The microphone and camera is in the train. It is going by the audible stop arms. This one's pretty, you can hear this one really well. Okay, what can we do now for... We are going to do this big kahuna equation here. It's going to take care of everything in one. We just got to keep track of what's moving and what's not. So let's see what you can do for homework here now. In this sound part, in chapter 17, you can do this first page of page 17 here. You can do this first page in 17, and then on the quiz, we did 1 through 11 previously. You can do 15, 17, and we could have assigned that before. 15 and 17, 19, 15, 17, 19. So we have 1 through 11, 15, 17, 19 you should be able to do. And we'll do a bunch of Doppler equations, calculations next time we meet. And it looks like I don't have very many Dopplers on here.